Okay, so last time we started to discuss the idea of the ray tracing, which is one of the basic ideas in terms of like doing some rendering in the graphics pipeline, and which is basically radically different the approach with the rasterization. So in the computer graphics framework, we can consider two very fundamental ways that we can basically render some 3D things into the 2D image. Like one is the rasterization, and the other thing is the ray tracing. So what we mostly just focus on in the introduction of the course was about the rasterization, basically projecting all the 3D polygons in the 2D plane and also doing some kind of the processing in the image space, image plane. While the difference with the ray tracing is that in the ray tracing, we are not basically projecting things into 2D, but actually it's the opposite, the other way around. We are shooting the rays from the camera center into the 3D space through the image plane in terms of that we are now fetching some color, many other the information from these 3D objects from the point where we are seeing some kind of the intersection between the ray and all these 3D objects. So in the algorithm-wise, what we could see as a kind of a difference is that in the rasterization, for all the triangles that we are having in the mesh, we are projecting them into the 2D plane, and then we start to care about some of the pixels that are included in each of the triangle, and then basically interpolating all the color depth and information, and then basically updating the final images when the depth that we are calculating is basically shorter than the depth that we are having in the depth buffer. So this was the high level of the algorithm of the rasterization, while the ray casting is kind of the opposite. So now for each of the pixels on the screen, that we are shooting the ray into this 3D space and checking the intersection point with the 3D objects and basically fetching all this information from the 3D scene. And ray casting was the case that we only care about the intersection, the hit point, the intersection point with the 3D space, while the ray tracing is kind of the more complicated the framework that is not just like checking the intersection with the ray and the objects, but actually kind of like back tracing all the paths of the objects by basically following all the secondary ray. So for each of the intersection the point, now we also basically see where the ray actually came from. So actually what we can see here is that it's more about some sort of the reverse engineering. So if we actually wanted to do some kind of the more like physically correct some kind of simulation for the light traversal, then we could actually start this kind of tracing of the rays from the light source. But then the problem might be that there might be tons of the rays that are not arriving into the image plane. So the computation will be very inefficient. So actually, that's the kind of the reason that we are doing some kind of the back tracing. So we are not starting from the light source, but actually we are starting from the camera point. And then we are doing some kind of the back tracing of all the trajectory of the lights in terms of that. And also for each of the intersection the point, we are seeing where the ray came from each intersection, the hitting with the objects. And then we are shooting all the secondary rays until we see that whether the ray arrives at the light source or the kind of the iteration, the recursion basically reaches to some kind of the maximum number. So this is the basic idea for the ray tracing. And once you basically back trace all this kind of the path of the rays for every single the intersection the point, we also shoot the ray into the light source in terms of that to calculate basically the color information for each of the intersection the point. So actually, as you can see, there are two main things. So when you see some kind of the intersection between the ray and these 3D objects, we should be able to basically compute the secondary ray, basically where the ray came from the intersection. So basically, calculating this kind of reflection at the point is one of the things that we are going to discuss in this course. And also for each of the intersection the point, we also should be able to calculate the color information by just like also fetching the information from the light source. So based on the materiality property for each of the objects and also based on the light information, we should be able to basically somehow determine the color information for each of the point. So that's also about basically some materiality properties of the 3D the objects, and these are also things that we are going to discuss in the rest of this course. So we also discuss many of the ideas in terms of like how we can really calculate this kind of the ray and the object the intersection. So we also did some kind of calculation with some kind of the plane and the triangle and sphere, and also with the implicit representation, we also discussed basically how we can calculate this kind of the intersection of the point. So those are basically very basic things that these are also the things that you will need to implement in the programming assignment. And then basically the question is that, so then the problem is that this is the case that we need to calculate the intersection between all the rays, basically for all the pixels in the image, and also for all these 3D objects that we have in the 3D space, we should be able to basically calculate all this kind of the intersection, which will take tons of time, especially if we have like lots of the triangles in the 3D space. So here the kind of the some technical the idea was that how we gonna basically accelerate this kind of the computation of the intersection. So one of the kind of simple idea is basically making some kind of the bounding volumes for some kind of the subset of the 3D objects, some triangles, in a way that we can basically facilitate this kind of the intersection, the computation with some kind of the simple geometry. So especially if we consider some kind of the axis aligned, the bounding the boxes, those will be the cases that we are having the 3 pairs of the slab for each of the axes. Then we can see the computation of the intersection becomes like much easier for those kind of the axis aligned the bounding boxes. Then the question is that how should we also define this kind of the bounding boxes? So we also discussed the 2 extreme cases. Like if we make like one giant the bounding box for the entire scene, the problem is that if the ray hits that bounding box, then there's no difference. Basically, we need to also consider all the objects in the scene to check the intersection with the objects with the ray. So that's also not that efficient way. And if you also consider like having the bounding box for every single the primitives, so that also does not make any kind of difference in terms of that. Still, we have the n number of the kind of the bounding boxes. Right? So here the question is that how we can make some kind of the some hierarchical structure of the bounding boxes or some kind of the, some bounding primitives in a way that we can do some kind of the more efficient the computation. So basically what we are going to do is that we are sort of like extending the idea of the binary search tree in the 1D search. So if we have this kind of the a sequence of the integer number, and if we want to basically query, when you have some kind of query number and finding some kind of the closest the integer in this the sequence, then how we are going to do this kind of the search in a more efficient way. So one of the ideas that we learned in the algorithm course might be using like having this kind of the binary search. So every time, like given the sequence of the integer, the number, we are taking the median number and making this kind of the 2 subsets. And for each of the subset, we also pick the median number and making the 2 subsets again. So in this way, we can make some this kind of the tree structure, and then basically this kind of tree structure makes the complexity of the computation to be log n scale, right? So here, basically, the idea is that how we are going to do the same thing, not only in the 1D space, but also in the 3D space. So for that, basically, we discussed the idea of the bounding volume the hierarchy. So this was basically the case that, like, we are splitting the one basically big, the bounding box into the 2 basically disjoint sets. So this is the case that we are having the this big bounding box. And we want to basically split this into the 2 disjoint sets of the primitives. So here, basically, one thing is that we are basically finding these disjoint the sets of the primitives. But for those kind of the cases, the bounding boxes of those sets can still overlap in the 3D space. So we are basically repeating this kind of like making some sort of the sub-bounding boxes in a way that we can build some kind of some binary tree in the 3D space. So for that, I mean, there can be some multiple ways to basically construct this kind of a tree structure. And what we can do basically is that for each of the steps, we first determine the axis that we are going to do some kind of the split. So we can basically choose this kind of axis as going to be one of the X, Y, Z axis. And then we can also start to make some kind of some candidates of the split, the planes. In the space. So this is kind of the 2D example that we are having some multiple kind of the objects in the space. And for this given the axis, for this axis, we are making some kind of the candidate the planes. So there can be also many kind of the heuristics in terms of like how we're gonna make this kind of the split planes. So this is the example that we are having some uniform the interval of all these split the planes, but we can also basically determine this kind of the candidates based on the shape of the geometry. We can first, for example, like make all the split the planes at the corner, like at the end of each of the primitives, or based on the centroid, or many other things. So there can be some kind of multiple ways that we can propose some kind of the candidate planes. Then here the question is that we are choosing one of the best plane that will basically somehow make some more efficient the search. So here the question is that how can you determine that which split is kind of the best split? So that was kind of the question. So what we discussed last time is that we discussed this specific example. So when you have this kind of the objects in the 2D space, and if we are finding some kind of some best split planes in terms of making the two bounding boxes, how are we gonna make this kind of split? So if we just like follow the idea of the binary search tree, that what we are going to do is that we might basically sort those things. So based on the order, we can see like this, like 1, 2, 3, 4, 5, 6, 7, 8. So we are having the primitives here. Then if we just follow the binary search, then we might want to basically split those kind of things by just having the one bounding box, which are basically having the half of the primitives, and the another the bounding box, which are basically having the another the half of the primitives. So this will be the example that you can see here. Having this kind of two bounding boxes, those are the cases that we are having the same number of the primitives for each of the cases. And that's actually what we have done in the binary search tree, right? So if we just follow that, then we're gonna have this. And as you can see, the problem is that now we are having like two big bounding boxes. So as we basically have the bigger the bounding box, there is like more chances that the rays would basically hit this kind of the bounding box, which means that we start to also investigate like all the kind of the primitives that are included in this bounding box. So for basically making some more efficient the search, kind of the important thing is that it's better to have some kind of the tighter the bounding box like this, right? So as we basically have some kind of the smaller the bounding boxes, there will be basically less chances that the rays basically hit each of the bounding boxes. Then we can easily ignore some kind of the all the primitives that are included in each of the bounding box. It is clear. So here, basically, the idea is that how we are going to make some kind of the split of the bounding boxes in a way that we can basically make some more kind of efficient search while having this kind of the tighter the bounding boxes. So there can be lots of the heuristics for that. One of the heuristics that we can choose might be that, so we can somehow define this kind of the traverse of the coast. So here, basically, the traverse of the coast means that we are having some kind of the cost of like visiting each of the interior the node. So basically, we can do some kind of the bounding box the test. And then now we care about like these two things. For each of the two subtrees, so we are going to have the two subtrees. We can calculate how likely a ray will basically hits each of the bounding box of the subtree. And also what's the kind of the cost of like basically traversing all the things inside each of the subtree. So these are basically two quantities that we can define, right? Does it make sense? For basically, we are having some kind of the constant the cost or like visiting each of the bounding box. And for each of the candidates split plane, we will be able to define the left subtree and the right subtree. And for each of the subtree, we are going to somehow measure like how likely a kind of random ray will hit the bounding box of the subtree, and also what will be the cost of like visiting each of the subtree. So somehow we are going to somehow approximate these kind of quantities in a way that we can define some kind of the traverse or the cost. Then what we can do is that given the set of the candidates of these split the planes, we can basically calculate this kind of the traverse or the cost for each of the plane, and then we can basically choose the one that is giving the minimum the cost, right? It is clear. Any question on this? Any questions? So yeah, I mean, this is kind of like one model in terms of like how we are going to measure the efficiency for each of these split planes. And we can basically model this kind of the cost of the traversal in this way. And here the question is that how we are going to also model this probability and also this cost for the subtree. There can be many other ways we can do this. Very simple, the idea that people typically use to construct the bounding volume, the hierarchy is that we simply we can approximate the cost of like visiting each of the subtree as the number of the primitives. So that will be the case that we want to basically not basically having this kind of like too many primitives for each of the bounding boxes, right? So we once the very simplest the way would be is that we are approximating this cost of like visiting each of the subtree as the number of the primitives that will be included each of the subtree. And here the more important part might be is that how we are also going to the measure of the probability that a random ray will hit the bounding box of each of the subtree. And for that, what people typically do is that people basically care about the ratio of the surface of the bounding boxes. So for example, like when we have, let me go back to the previous slide. Yeah, so when we have this kind of the cases, we're gonna have this kind of the sort of the parent node, the bounding box of the parent node, and we're gonna also have the bounding box of the subtrees, right? And for each of the bounding the primitives, here the bounding primitives at the boxes, right? We can basically measure the surface of the bounding boxes. So when the Sn is the surface of the bounding boxes of the parent node, and the Sa is basically the surface of the bounding boxes of the one of the subtree, the A subtree, we are basically using this as kind of the ratio of like how likely the ray basically will hit this bounding box when the ray basically comes into this kind of the bigger the bounding box. So using this kind of the ratio of the surface of the bounding primitives, it's kind of the one very simple heuristic that we can use. And this kind of the idea is called the surface area heuristic, which is also assuming that the rays are basically randomly distributed, and also there's no closure in the space. So when you have this kind of the assumption, then we can simplify the kind of the approximation of the probability, how likely the ray will hit each of the subtree based on the kind of the ratio of the surface area of the bounding boxes. And that can be kind of the one simplest kind of way that we can somehow measure the traversability cost. So it turns out that this kind of the traversability cost becomes like this formulation. So we are having some kind of the constant cost, and for each of the ratio of the surface, we check how many kind of the the primitives are basically included for each of the bounding box. So that means that we can, given a candidate set of the candidates of the split the planes, we can calculate this kind of the traversability cost for each of the plane, and then we can choose one that is giving the minimum cost. So that's kind of the very typical the heuristic idea in terms of like building the bounding volume hierarchy. Any question on this? So I know that in our the programming of the assignment, there is no such part or like making some sort of the data structure that can make the rendering process to be more efficient, basically reducing the computation of the intersection. But if you are interested in, and I also recommend you to try to implement the bounding volume hierarchy in terms of that you can also render very large scenes with the lots of kind of the objects in the scene. Basically accelerating this kind of computation with this kind of structure. Any questions? Clear? Yeah, so this was kind of the one example that we are making some kind of the hierarchical structures by basically splitting the primitives in the space, basically making some kind of the two sub kind of the sets of the primitives in the space. But actually the other way around, making some kind of some specialty data structure is actually not dividing the given set of the primitives, but actually dividing the region in this 3D space. So the left is kind of the example that we are having the bounding volume hierarchy. This is the case that we're having the disjoint sets of the primitives. So as you can see, we are having this kind of the blue set and the yellow set, and blue are basically the sets that are including this kind of the left side, the primitives, and we are having another set. But this is the case that the bounding volume of each of the subsets can overlap in the space. So this is basically the one example. And the other way around is basically partitioning the space. So now we are having the disjoint sets of the regions. So we split the space into using this kind of plane in terms like making these two other disjoint the bounding box in the space. But then the problem is that here the one primitive can belong to the multiple the sets. So this is not the case that we are basically partitioning the sets of the primitives, but partitioning the space. So one of the famous example for this might be the KD tree or the oak tree, many other things, right? And in terms of like utilizing these kind of structures in the ray tracing the framework, what would be kind of the pros and the cons? Can you guess? The first question, when you use these different structures of the some hierarchical the data structure, what would be kind of the pros and the cons? And also the question was that cost of the ray primitive intersection is also calculated by the bounding box test. Yeah, so it also depends on how we define all the things, but at the end of the all the things, like at the leaf node, if we have like bounding box for like one single primitive, then that can be also the things. And also at the end, we will need to basically have the some computation like checking the intersection with the ray and the primitives in the leaf node. So that should be included in the leaf node. So let's think about some scenarios where like one of those kind of structures can have some more the advantages over the other one. Yeah, so actually my question is that in which case like one can be better than the other? Let's think about some cases. Any ideas? Yeah, so there might be many specialty cases that one can be better than the other. For example, like as someone also mentioned in this like we have some like really two very disjointed set of the primitives. Like we are having like one set here, like having some one set of the primitives on the left hand side, and also the other set of the primitives on the right hand side. It can be more efficient that we are having these kind of the two bounding boxes instead of like partitioning the space, right? So this can be better way that we are really making some kind of the tight the bounding boxes. So depending on the arrangement of the objects, actually one can be better than the other, right? But also one of the some specialty cases is that actually the one question is that for each of the cases, let's say we are making some kind of the binary tree, which means that each of the intermediate the node will basically have some kind of the two children, right? Two children node. But here the question is that let's say we check that the ray is hitting the one of the children node, then can he just ignore the child node? For example, in this case, let me try to shoot a ray, for example, like this. Yeah, I don't know if you can see. So yeah, as you can see, like this is kind of the ray which is coming here from the outside of the box and just hitting the yellow, the triangle. And what we can see is that, like, let's say like we first check the intersection with the ray and this wrapped the bounding box. And we're gonna basically see some kind of the intersection with this ray and this bounding box. But as you can see, actually, at the end, like what you can say is that the object, the primitive that should have the first intersection, the point with the ray, should be this yellow triangle, not any of the blue triangle, right? But still, we are seeing some kind of the intersection with this kind of the left bounding box, because we are also not partitioning the space with the bounding boxes. So which basically means that there are lots of the cases, like when you shoot the ray and when you find some kind of the intersection with the one of the children node in the bounding volume the hierarchy, actually there is a chance that actually the ray will have some kind of intersection with the primitives that are not included in the left set, but actually in the right set. Which means that since the bounded boxes are not basically partitioning the space, we should not just ignore the bounded boxes in the same level. But we need to do this kind of the intersection the checks with all the bounding boxes in the same level. While this is not true for the space partition in the case, since we are partitioning the space, if we find some kind of intersection with the one set of the children, the one of the basically the children the node, then we can immediately basically ignore the other the child node. So that's basically kind of the difference between these two. So which means that for most of the cases, except for some kind of the extremity cases, except for some of the extremity cases that we are really having some kind of the very sparse, some groups of some kind of the primitives. For many of the cases, it is known that the space partitioning can be more efficient in terms of that we can terminate the search after we see some kind of the first hit of the bound boxes. But the problem is that when you start to have some kind of some dynamic scenes, so for some of the cases, when you have some kind of the animation and all the primitive is basically be moving in the space, then the problem is that we will need to basically reconstruct all this kind of the bounding about the hierarchical structure for the space partition in the case. While in the case that we are having the primitive departitioning, when you still have some kind of some dynamic movement of all the primitives, we can just keep the same the hierarchical structure. So that can be kind of the good in terms of that we can when you have some kind of the dynamic the scenes, the bounding volume the hierarchy can be more efficient in terms of that we don't need to reconstruct everything. So those are kind of some pros and cons, and there are many kind of the other pros and cons. So we can also discuss those things later. Any questions on this? Is this clear? No question. Okay, so if there is no question, let's move on to the main topic that we will need to discuss for today. This was. Okay, can everyone see my slide? So let's discuss the main topic for today, which is the radiometry and the photometry. So those are also the things that we briefly also discussed in the introduction of the course. But these are basically very basic the terminology that we will keep utilizing for all the discussions in the rest of the course. So you will need to get familiar with all the terms that we are discussing for today. So as I also mentioned at the very beginning, basically we are discussing this, ray tracing the system. And here the key thing is that basically how we somehow model this kind of the reflection of the rays. So how are we going to determine the direction of the secondary rays, and also how are we going to determine this kind of the color and all the information from the combination of the material information and also the light source information. So those are basically the main things. And for that, like what we are going to do is that we are doing some kind of the optics simulation. as much as possible. Obviously, the simulation that we are doing may not be that, very physically correct, some kind of the approximation, but it's kind of like approximation. So we are going to basically discuss some of the terms that are used in the optics and see how these terms will be basically calculated in some kind of the simulation, the setup. So those are basically main things. So as kind of the first step to basically model all this kind of like reflection of the things, basically modeling this kind of illumination, we are going to discuss some terms that are basically typically used to basically measure some of this kind of illumination in the lighting. And basically we're also going to discuss some of the units to measure those things. So there are basically four main quantities. And as you can see, these names are basically quite confusing, very similar, but you need to get used to the difference of like those kind of the terms. So we are first going to discuss the radiant flux, which is basically about the power, and the radiant intensity is basically about the power per power, per unit the solid angle. So we're gonna see what's the meaning of the solid angle, but it's basically more about some kind of direction of the light. And irradiance is not the power per the solid angle or the direction, but it's more about the power per the unit area. So this is another term. And also the radiance is basically the power, the flux per unit area, and also per unit solid angle. So those are basically the four main terms that we are going to discuss for today. So keep this in mind. So what's the kind of goal of the like having the four terms? So all the kind of things about the radiometry is to do some kind of the calculation of the lighting in a physically correct the manner. While we are having some kind of some of the assumptions here, and obviously we are assuming that lights are basically traveling in the straight lines. So basically this is assuming that lights are basically traveling in the empty space, and there is no influence by some kind of gravity or the things. So basically all the lights basically travel in the straight lines. And obviously we also assume that all the objects have the size which is like much larger than the wavelengths. So if we have like very tiny, small the objects, then all the assumptions that we are having here might be just broken. So we are also obviously assuming that the objects are like big enough compared to the wavelengths, which is like very tiny kind of things. And we don't model any kind of the deflection or the interference. We only care about some kind of reflection, the model that we can typically see. So those are the assumptions for the radiometry. And let's also briefly see how the light basically works. I mean, those are some kind of the basic things might be in the physics, but this is not the physics course. So we are not gonna get into the very much details for all the things. But very high level, some kind of the assumption here is that basically all the lights are basically generated by basically consuming some energy. So what we are going to see is that basically lighting is kind of the process that we are consuming the energy in terms of that some of the energy is turned into the heat, and some of the other part of the portion of the energy is basically turned into the photons, which are basically delivering some kind of the amount of the energy through the light. So this is the basic assumption. And what we typically do in the computer graphics is that we just assume that the ratio of these two, basically turning the energy into the heat and also turning the energy into the photons, is basically constant for each of the light source. So we don't care about like how this kind of ratio is basically changing over time, but for each of the light source, we are having the ratio like these two, turning into the heat and also turning into the photons, which means that the power which is delivered by the photons will be basically proportional to the kind of the energy that we are consuming to generate the lights. So for this reason, we are going to use two terms, power and the energy, as kind of interchangeably, because these are basically some kind of the proportional the quantity in the lighting. Oh, you are still seeing some old slides? So you are not seeing this slide for the lighting? Oh, sorry. Let me stop sharing and just reshare. Why this is okay. Can you see this slide now? Is this different slide with what you have seen before? Oh, let's see. Oh, yeah, thank you for letting me know. I didn't know that. So yeah, so let me then briefly go back to the previous slide. So yeah, so I was basically saying that these are basically the terms that we are going to discuss. Uh, yeah, by the way, like you can also find these slides in the link that I also posted on the Slack. So you can also check out those slides as well. So those are the four terms that we are going to discuss. And then, yeah, so we are having this kind of assumption, like the light surface traveling in straight lines. Obviously, the object has the bigger size than the wavelengths and no modeling for the deflection and the interference. And yeah, so those are things. Basically, we are going to assume that like when we basically the kind of the light source, like the light bulb, is consuming the energy, we are having the constant ratio of the photons that are also basically delivering this kind of some portion of the energy into the light. So in this region, I mean, in terms of that, we are having the constant ratio that we are turning the energy into the heat and also turning the energy into the photons. We are going to basically interchangeably use these two terms, power and the energy. So power is basically the energy which is basically delivered by the light, and here the energy basically means that the amount of the energy that we are consuming to generate this kind of the light. So this is basically the basic the assumption. And also the other thing is that we are also going to discuss some different terms, like also interchangeably in terms of that. So what we are going to mainly discuss is some terms that are defined in the radiometry. So radiometry is all about basically the power of the light, or some kind of the quantities that are basically defined based on the power of the light. So those are kind of the quantities defined in the radiometry. And the photometry is kind of different in terms of that these are some quantities that are defined based on the brightness that is really recognized by the human eyes. So those are like all about the brightness, the photometry, and the radiometry is all about the power, which is delivered by the light. But also the thing is that for all the quantities that are defined in the radiometry, we're gonna see that there are some kind of the counterparts that are defined in the photometry. So you can see this kind of the different names that are kind of like indicating similar thing. So those are kind of the basic things. So the things that we are going to discuss from now might be a little bit boring in terms of that I just keep saying some kind of the new terms. But yeah, you will need to get used to those kind of the terms to discuss the rest of kind of things. So I also recommend you to check out these kind of the definitions after the lecture and see and what's kind of the differences. Okay, so let's first get into the radiant energy. Energy is basically just nothing, basically the energy, which is really delivered by the light. And also the energy has the unit of the joules. This is basically the things that we are also seeing in the physics. And when you also talk about the radiant difflux, which is about the power, which is basically the energy, which is either emitted or reflected or transmitted or received per unit time. So this is basically some energy over the time. So this is the flux. So basically for the power or the flux, we are having the unit of the watt, right? So this is basically the unit that we are typically using in the radiometry, and the counterpart of the unit in the photometry is the lumen. So those are basically two different kind of the things. So when you talk about the radiant difflux, the same kind of the quantity, some corresponding the quantity in the photometry is called the luminous flux. And for that, we are having the some quantity, the unit of the quantity, which is the lumen. And here the question is that then are these two the same? So if we have some kind of the 10 watt sort of the light bulb, then is it the case that we're having the 10 lumen? Obviously, no. As I said, like the watt is basically the unit for the energy, basically for the power, and the lumen is basically the unit for the brightness. But we are basically assuming that kind of the ratio of like these two will be the same for each of the light source. that also means that if we have like different light source, so depending on when you have the LED bulbs or some kind of fluorescent the tubes, there can be some more efficient the light source, which is making brighter lights with the while consuming the same amount of the energy, right? So that might be the case that we are using the smaller the amount of the power basically while making some kind of the brighter the light. Or there can be some kind of like less efficient kind of the light source, which is basically making the same the brightness of the light while consuming the more energy, right? So depending the light source that we are having, there can be some kind of the ratio between these kind of the two units, right? So if you actually buy some kind of the light bulb, then you can check out the how much of the white the watt is consumed while making how much of the lumen of the brightness the light bulb is basically generating. So those are basically two things. And based on these two quantities, you can check out the kind of the efficiency of the light bulb. Does it make sense? So this is the basic thing, the radiant flux, which is about the power of the light. And then we are going to discuss some kind of the different things in terms of like the intensity, which is about the power per each of the direction. It's basically about like the per direction or the per solid angle. And also we can think about the light, which is like falling on some kind of a specific the point over the surface. So it's about the per the surface, per kind of the area. And also we can think about some basically the light, the ray, which is traveling in the space, which is the radiance, is the per solid angle and per the area. So we're gonna get into those things. So the next thing is about the radiant, the intensity. So basically intensity is now the power over the solid angle. And the solid angle is basically about the kind of the direction. And so, and also we're gonna see this solid angle has the unit of the stir radian. Stir radian. Yeah, we're gonna see like what this basically means. And it will basically divide the lumen by the stir radian. Then we get the another kind of new unit for the photometry, which is about the candela, which is about the intensity. So here the question is that what's the solid angle, right? So we know the angle. So we are going to extend the concept of the angle into the solid angle. So when you basically talk about the angle, which is basically the ratio between the length of the arc, which is basically subtended by the angle here, with the radius of the circle. So let's think about like this the circle here, right? Then if we define any kind of the angle like this, then we're gonna see some kind of the arc, the curve here, which is basically subtended by the given the angle, right? Which means that for each of the angle, we're gonna have some kind of the corresponding the length of the arc curve, which is defined by the subtending this kind of the given the angle, right? Then if we basically measure the ratio of this like the length of the arc curve with the radius of the circle, then this becomes some kind of the unit of the angle, right? So this is the quantity which is defined as the radian, right? It is two. So basically, a circle has the 2 pi radians, and for any kind of the angle, we can basically have the radian as kind of the unit for the angle, which is basically calculated as the length, the ratio of the length of the arc curves and also the radius. So middle school kind of things. So what we are going to do is that we are going to extend this thing into the for the 3D sphere. So this was the case for the 2D circle. So if we extend the same thing for the 3D sphere, now we can also think about like having some sort of the angle, which is actually the solid angle, which also will basically be extended into some kind of the not a kind of the region here, but into the volume, right? So we can think about a kind of the cone, which is defined with some solid angle, right? That will be projected over the 3D sphere. Then we can also define the region over the sphere, which is defined as kind of the which is the subtended from the given the some sort of the solid angle here, right? Then, as we have done for the angle case, now we can also define the unit of the solid angle as kind of the ratio like of this area, which is subtended from the given the solid angle over the not the radius but the squared radius. So now this becomes some kind of the unit of the solid angle. So you can say that solid angle is kind of the angle for some kind of the cone in the 3D space. And now we can have some kind of the unit of this solid angle by calculating this ratio, like A is the area which is subtended by the given the solid angle over the basically square the radius of this sphere. So that becomes the definition of the solid angle. And what we can see is that since the surface of the sphere is 4 times pi times r squared, then which means that the solid angle of the sphere will be 4 pi, right? So we're gonna divide this by r squared. Then we're gonna have the 4 pi the steradian, which is the name of the unit, the solid angle. It is clear? Any question on this? Clear? Yeah. So what we can see is that let me give you some kind of example. So we are on this peak, the Earth. There is a moon and the sun, right? I don't know. It's way far from the moon, right? And actually, we can also see some kind of define some kind of the cone like this, making each of the moon and the sun as kind of some kind of the objects that is defined as kind of some sort of the section of the cone here, right? So actually, let me give you some better figure than this. So like even this kind of the Earth here and the moon and the sun, we can also define some kind of the solid angle, which is defining some kind of the projection of each of the moon and the sun, many other things over the Earth. And this kind of projection actually can be defined with the solid angle. So the also interesting thing is that if we really calculate the solid angle, which is like subtended by the sun and the moon, we can actually see that the solid angle of these two are almost the same as the 60 microvistoradians. And where can you see this kind of the evidence that these two solid angles are almost the same? We know those kind of things, right? When can you see this kind of the evidence that these two actually the solid angles of the sun and the moon are almost the same? No idea. Have you seen the solar ellipse, the total ellipse? When we see some kind of the cases of the total ellipse, you can see that actually the sun is totally occluded by moon while making some kind of the very thin ring, right? Which means that sun and the moon are basically having almost the same the solid angles, basically making the almost same the projection the area over the Earth, which is very interesting, kind of some natural kind of the phenomenon, the fact. Yeah, so that's kind of thing. So that's kind of thing. So we are basically having almost the same the solid angle for the sun and the moon. So which means that if we know the surface area of the Earth, then we can also calculate the region, the area of the region of the projection from the sun and the moon, which will be almost the same. So can you quickly calculate those things? What will be kind of the area of the projected the region of the sun and the moon? yeah, maybe I can go a bit quickly because we have many things to discuss for today. So like this will be the case that like 4 pi is steradian, we will have the 510 million square kilometer, which will be should be the same with the 60 micro like steradian with some kind of the area, right? So if we basically calculate these things, then what we're gonna get is that yeah, this kind of the amount of the size of the region, which is like 4 times bigger than Seoul or Daejeon. So quite big region, right? So we can basically do this kind of a calculation. So based on all these solid angles, actually we're gonna do many kind of the calculations. And so one of the calculations that we're gonna do is basically having some kind of the differential the solid angles. So when you have some kind of like utilize the spherical the coordinates for the surface over the sphere, we can define the differential the area like this, right? So if we utilize the spherical the coordinates, yeah, the differential the area over this the sphere can be calculated in this way by just like multiplying r times d theta here, and the r sine theta d pi, which is by defined here. Basically, this length, this length and this length can be multiplied to define the differential the area, which is defined like this. And based on that, we can also define the differential of the solid angle, which should be differential area divided by the square, the square of the radius. Then we're gonna see that actually differential of the solid angle can be calculated as this form by multiplying these two angles and the sine the theta, right? And also for the rest of the kind of the part of the slides, we're gonna basically use this kind of omega as kind of the some mathematical denotations to denote some kind of directionality vector. So actually also what we can see here is that if we have some kind of the light source, which is like emitting all the lights with the uniform the intensity into the only direction, then what we can see is that, and also when we see that this is the amount of the flux which is emitted by the light source. So let's think about that. We are having some light source, which is having this pi amount of the flux and also emitting the light into the some uniform the intensity into the all direction. Then we can calculate this uniform intensity as kind of the pi over the 4 pi over the 4 pi, right? So this will be it can be computed based on the our definitions of the solid angles, right? Clear? Some questions in the chat. Yeah. And so we can really do some kind of some very practical calculation. So when you see some kind of the light bulbs, which is saying that has the 815 d lumens, then how can you calculate some kind of the intensity for that, the candela? So the way that we can calculate the candela is that if we assume that the light bulb is basically emitting all the lights into with uniform the intensity, then we can simply divide this amount of the flux by the steradian. Then we can calculate the intensity like this. Here, like one quick question is that, then let's think about some special case where the light bulb is not emitting the light into the uniform intensity into all the directions, but somehow if the light is basically making some kind of a cone-like shape, which is like concentrating all the emission of the light into the some cone, with the diameter of the angle is kind of 20. So let's say we're having the light bulb here. Somehow this light bulb is basically like emitting the light into only into this kind of a cone. Then how can you compute the intensity in this case? So this is the question. And actually, you realize that this computation is not very simple because the quantity of the steradian is defined based on the area over the surface, right? So which means that when you also define some kind of a cone with the angle the theta here, we should be able to compute the area of the this region which is basically making some kind of the defined based on the intersection of the cone and the sphere, right? So this kind of a region, which is defined based on the angle here, and also the radius here, is called the speaker cap. So if I give you some kind of the hint in terms of how we can calculate all the things, this area of this speaker cap can be actually just simply calculated as kind of the 2 pi RH. Here the h is this length. And since we are having the angle theta here, the diameter of like actually the radius of the radius angle of the cone, actually you can see that the h is the same as the r1 minus cosine theta. Then we can see that actually the area of the speaker cap becomes this, right? So from this, actually, we can calculate the intensity for the cases that when the light is basically concentrated into the the cone with the 20 degree, so yeah, of the cone, right? Then based on this fact, can you calculate this? So let me give you the hint. So if we know this fact, the speaker, the cap has this area, then based on this, can you calculate the intensity here? Yeah, I mean, maybe you can really just calculate the final number and see what you get. Yeah, obviously that would be basically 815 over like 2 pi, like, 1 minus cosine 10 degree, right? So if you calculate this, then what you get is that actually I just calculate this using the ChatGPT and it was giving me like this, right? Which is basically, sorry, yeah, way higher than the intensity that we can see when the light is basically emitted with the same intensity, right? So yeah, we can do all this kind of the calculation with the stuff, I mean, the solid angle and many other things. Any questions on this? So we discussed the flux and also the intensity, which is like flux by the solid angle. So those are basically two quantities. And we're gonna also see the definition of the irradiance. Irradiance is not the power per the solid angle, but actually the power per the unit area, which is like coming into the over the surface. So we're gonna basically compute this term in terms of basically calculating the amount of the light, which are basically arriving at the same point over the some kind of 3D space from all the directions. Basically, the light can come from all the other directions, from the all different sources, or even from the reflections from the many other objects. So this is basically the quantity that we are basically defining as kind of the power per the unit area. And now we are also having some kind of the unit for this, lumen over the security meter, which is now defined as the lux here. And also you can see some kind of the typical number of the lux for the many kind of things. So the sunlight has like more than 100,000 lux, and some kind of this in the sunrise, it is decreasing until like 40. It's very small, right? And also the moonlight even having the like even smaller than the 1 lux. It's very so you can see that the sunlight is like way much brighter than the moonlight. So we can have this kind of the quantities for the radiance. And also when we talk about like relators or all those kind of things, like one kind of the important thing is basically the Rambert's the cosine law. So what we can also see is that, let's think about that we are having the same kind of the light source, which is kind of the making the flux with some kind of the beam of the light. So let's think about that we are having this kind of sort of the some area light, which is in the having the same area of basically emitting the light. So making some kind of the cylinder like the beam in the space, we are receiving this kind of light in over the plane like this, right? So then what we can see is that when we basically have this kind of the direction of the light, which is basically perpendicular to the plane, then the amount of the radiance that we're gonna get would be basically when this pi is kind of flux and a is the area, then the radiance will be the pi over the area. So this will be basically radiance that we're gonna get. So this is basically the power per the unit the area over the surface, right? But what you can see is that if we basically have some kind of the slanted angle of the light is emitting to the surface, while this direction is not the same with the normal direction of the plane, but having some kind of the some slanted angle, then we can see is that for the same this kind of light source with the same the area of the light, actually this light will basically cover the bigger region, right? As we basically have some kind of some tilted the direction of the light, this kind of light source will basically start to basically cover some kind of bigger region, which means that when he measures the radiance, which is the flux per the area, per unit area over this sphere, over the surface, as we basically the light is basically covering the larger region, which becomes like larger as kind of the A over the cosine d theta. Basically the radiance for each of the region will be decreased. So that's basically what we typically see. Does it make sense? So as we basically somehow change the direction of the light in terms of that the light is basically not seeing the plane in the kind of the perpendicular direction, but with some kind of some slanted angle. The area light will basically start to basically bright the bigger region, which means that for each of the some kind of the unit area, the amount of the light the surface is basically receiving will be decreased. And the amount of the decreasing can be calculated as kind of the one over the basically as kind of cosine d theta, right? As some kind of the projected the surface here will be increased as kind of the A over the cosine theta, right? So which means that as we basically have some kind of some slanted the angles of the light source coming from the kind of space into some bigger the surface, we're gonna see that the irradiance is basically being decreased with the amount of the cosine d theta. So this is the kind of the law which is called the Lambert's the cosine law. And this is actually one of the reasons, actually the main reasons that why we are having the seasons now. So we are in the spring season, and we also see have the winter season. So when you have the spring season, then we can see that actually the direction of this kind of the surface normal here and the direction of the light coming from the sun, basically this angle is basically kind of small, which means that we are more like directly getting all the kind of the energy of the light. So which means that we are getting some kind of the more kind of the power of the light. But when you basically have this kind of the winter season, where basically the angle between the surface normal and the light direction becomes larger, then the radiance per each of the region will be decreased. So we are basically gaining some kind of the less amount of the energy for each of the region. Then we are basically having the winter. So this is kind of the reason that why we are having the season. So also the fall off, as we basically, so let's think about that we are having the light, which is light source emitting the lights. So when you receive the light with some kind of a smaller the radius like this, or when you receiving the same light with the bigger the radius like this, obviously as we get further and further from the light source, the energy of the light that we are receiving for each of the the region over the sphere will be decreased. So which means that the irradiance will be decreased as we basically get further from the given the light source. Any question on this? So we discussed flux, which is about the power, and the intensity, which is like flux over the solid angle, and this is the irradiance, which is like flux over each of the area. And the last term that we are going to discuss is the radiance. So radiance is basically the power emitted, reflected, transmitted, received by a surface per unit solid angle and also the per area. And also this basically has the unit of that which is dividing the lumen by the steradian and also the square meter, which becomes the nit. So this is basically another the kind of the unit for the in the photometry. But here also the key thing is that we are not basically just like having this kind of quantity for just the per area, but actually we are having this quantity per the projected area. So that's basically why we are also having the cosine theta here. Yeah, so we are not just having this like dA here, but dA the cosine theta. This is basically based on the same reason of the Lambert the cosine law. So here, this is not the case that we are basically for the having the same radiance, same the flux. This is not the case that we are basically changing the region to be covered by the same the light. But while this is actually the case that while we are having the same dA, how much this kind of the solid angle of each of the light from the different directions will be changed. So while actually we are having the so kind of the different way to interpret this. Actually, in my understanding, is that in having this project area is basically the same that we are having the same dA, same kind of differential of the area while basically adjusting, the solid angle for each of the direction. So what we can see here is that if we basically have some kind of this slanted angle here while we are fixing the differential of the area here, then what we're gonna get is that actually this will be the case that we are having this projected the area which is perpendicular to the light direction, and this perpendicular the projected area will be dA the cosine d theta, which means that if we fix the differential area to be dA, this will be the case that we are decreasing the solid angle to be d omega to the cosine d theta, right? So based on the angle that we are seeing the same region, we are also adjusting. So this can be interpreted that we are basically defining the either define the radius t based on the project area, or we are having the same the differential area while adjusting the solid angle as the by multiplying the cosine theta. So that's basically the definitions of the the radius. So keep this in mind that we are basically having this quantity as kind of the per unit solid angle and also the per unit the projected area. So that's why we are having the cosine theta here. Yeah, basically the idea came from the Lambert's the cosine rule. So yeah, these are also some kind of the common the quantities, the numbers of this quantity. From the sun, we are having the what's that? Billion, 2 billions of units, while we're also having some very small kind of units from the moon. And also we can think about like two types of the radiance. Like one is kind of the like incoming incident radiance. So for each of the region, we can basically think about basically having some kind of the incident the light from many different directions. That will basically be contributing to calculate the radiance at one point, right? So for each of the point, we're gonna have this kind of like incoming radiance, which will be basically used to calculate the irradiance at each of the point. And after the reflection, we will be also able to define the exiting radiance, which is now amount of the light, which is basically also leaving the surface into some specific direction. So basically, we are having the two types of the radiance, which is like one is about like incoming the radiance, and the other is about like the exiting the radiance. So the reason that we are basically talking about those kind of things is that we really need to differentiate like these two. So when you basically have this kind of like incident the radiance for some specific direction, it obviously does not mean that we are also basically emitting the same amount of light into some specific into the same directions. So what we are going to do for all the rendering the process is that we are going to accumulate all these kind of the incoming radiance from all the different the directions, and based on our some kind of the refraction the model, we're going to also calculate this kind of the outgoing the radiance as kind of some with some kind of calculation. So basically, we're gonna distinguish the incoming, the incident radiance, and also the exit radiance based on our the formulations. Any questions on this? So yeah, radiance is kind of the main thing. It's the fundamental, the quantity that basically characterizes like all the distribution of the light. And also we are obviously assuming that the radiance is basically invariant along the ray. And all the rays are basically moving like straight like in a straight line and basically delivering the same amount of the radiance over the space without basically assuming that any kind of the occlusion in the space. And what we are going to do with the so-called the rendering equation is basically all about basically calculating this kind of the radiance or the irradiance over the space that will basically change basically with some kind of the reflection with the ray and the objects. And then by accumulating all this kind of the some changes of the radiance, we're gonna basically get final the rendered image. And these are the quantities that we discussed. So given the energy, we also define the power, which is the energy over the time. Intensity is the power over the solid angle, and relatedness is basically power over the unit, the area, and also the radiance was basically the power over the project area and also the solid angle. And for those kind of cases, we also have some kind of the counterparts in the photometry the field, and also there's some kind of the units that are defined based on the brightness. Any questions on this? Yeah, so before we end the 2 days lecture, let's just briefly see one more thing. So let's see some kind of a simple example, like how we're gonna determine the irradiance based on the information of the incoming irradiance, right? So what we can see is that basically we can calculate the irradiance from the given the information over like the radiance over all the directions, right? So when you think about like one single point over the sphere, and when you basically assume some kind of a flat plane, so that we can consider only the hemisphere for all the directions. So over all the directions, like defined with this kind of point over the hemisphere, if we can have some kind of information about the incoming irradiance, then we can basically calculate the irradiance as kind of the integral of like this form, right? So we have the cosine theta here because of the definitions of the radiance, right? So we're gonna also call like this kind of the term the amount of the radiance times the cosine theta and the solid angle. This is kind of the differential the irradiance, which can be used to calculate the final the irradiance, right? So what we need to do is that we are taking the integral of the differential the irradiance over the hemisphere, and this differential the irradiance is now defined as kind of the multiplication of the irradiance and the cosine theta and the solid angle, right? So this means that if we assume some kind of the constant, the incoming irradiance over all the directions. So let's say L is basically the constant, the incoming irradiance from all the directions. Then we can actually just calculate that. So end of like all this calculation, we can say that then the irradiance, by accumulating all the things, can be now calculated as kind of the L times pi. So these are some types of the calculation that we are going to do in the rest of the course. Any question on this? Please? Yeah, so we discussed some kind of the multiple the terms, the terminology of the radiometry, which might be quite confusing, like these very similar names like radiant flux, intensity, irradiance, and the radiance. Those are like all very similar the names with some kind of the different, some kind of units for each of them. But it's also important to see that we are basically why we are having this like the cosine theta term, which is coming from the Lambert cosine rule, and how we also define the solid angle, right? These are also kind of the basic kind of the things in terms of like defining those things. So what we are going to do is that given some kind of some information, as you can see here, given the information of the incoming radiance, we're gonna compute the radiance, and based on that, we're gonna also calculate like outgoing the radiance based on some kind of the metrology properties. So what we are going to do for the rest of the course, we will be like doing all this kind of the calculation based on those quantities, and how we're gonna also kind of like make it efficient to calculate all those kind of things in some kind of the discrete manners. So that's kind of the basic ideas. So I strongly recommend you to get used to basically all these kind of the names and the concepts of those quantities, so that we can discuss more about the rendering equation in the next time. Any questions? Clear? So yeah, if you have more questions, please feel free to ask the questions on this Slack. From the next week, we are going to start to discuss some metrology properties and also the rendering equations. So how exactly we're going to calculate all these kind of quantities in the ray tracing system. So I'll see you next Monday. Thank you. Bye.